And now I get to introduce you to a friend who has visited us here at KAUST twice, who caught the KAUST vision very early, and who helped me appreciate the KAUST vision during my last year at Columbia University when we were both there and when I was trying to decide whether to come here. Professor Mona Diab conducts research in statistical natural language processing, a rapidly growing, exciting field of research within artificial intelligence and computer science. Interdisciplinarity is inherent to NLP, drawing on fields of algorithms, software engineering, statistics, machine learning, linguistics, pragmatics, and information technology. It's both, let's say, hard sciences and humanistic, and it's a very exciting intersection. Professor Diab's NLP lab addresses problems in social media processing, building robust enabling technologies such as syntactic and semantic processing tools for written texts in different languages, information extraction tools for large data, multi-level processing, machine translation of language, and computational socio-linguistic processing. Professor Diab has a special interest in Arabic NLP, where the emphasis has been on investigating Arabic dialect processing, which we heard about in the earlier part of the afternoon, where there are very few available automated resources. Professor Diab is at George Washington University in Washington, DC, but for most of 2020, limited as we have been from traveling in 2020, she has been a research scientist at Facebook AI in Seattle, the other Washington, not Washington District, but Washington State, from the East Coast to the West. She hails originally from Egypt, but also has spent some years in Saudi Arabia, so she knows very well our context. She has 2 bachelor's degrees, one from Helwan University and one from the American University in Cairo, AUC. She earned her master's at her current employer, GWU, and a PhD at the University of Maryland. Professor Diab has founded some long-lived research groups, including one of the ones that our first speaker belonged to when they worked together at Columbia, the CAMO project. Her 250 or so papers together generate an average of about 100 citations per month, or about 1,200 per year, and are growing steadily. The field is in ascendancy. This is not me, as far as I know. I don't know what that is, but finally, Professor Diab regularly delivers keynotes at major professional meetings, and so we are delighted that she recognized the value of accepting our keynote invitation at KAUST today. So next time, Mona, in person, I hope, but today, thank you for joining us virtually with the Northern Lights behind you. And if you can now assume the control of this Zoom session and share your slides, we're absolutely delighted to hear from you. So thank you all everyone who's here. And Mona, welcome to KAUST again. You are still muted.
Hello, hi. Can you hear me?
Yes.
Excellent. Oh, thank you very much. Thank you very much for this very generous introduction, and it's really truly a privilege to be here. And sorry if I sound a little bit incoherent. It's still 6 o'clock in the morning my time, as David had mentioned. So, but I wouldn't have missed it for the world. I really appreciate the invitation, and thanks a lot for putting this together. And it looks like a very impressive workshop. Unfortunately, I missed the better half of it probably, but hopefully I'll share with you some of my ideas and so on. But one note I just wanted to highlight, if people don't necessarily know this, but the majority of the early years of computer science was initiated by women. Because it was considered the soft sciences as opposed to the hard sciences. So this is kind of like a missed piece of information. So women have tended to have an impact on this field as well. So, but now hopefully this would be more recognized. So today I'd like to talk to you a little bit about addressing low resource scenarios through the lens of Arabic as an NLP microcosm. What are the challenges and opportunities? So, let's see, where am I? Actually, which screen do you see? Do you see my projected screen? I'm not sure.
Yes, we're seeing the three screens. The next slide and
oh, so you're seeing the wrong screen. Sorry, let me make sure that there's something. Share. It's you want to be sharing this one. Okay. You see, I've given a lot of keynotes and a lot of talks, and I still don't have it mastered Zoom yet. So this is another challenge.
Yeah, the intersection of Zoom and PowerPoint is still a difficult one.
And multiple screens, yeah. So actually, now are you seeing my projected screen? Just double checking.
Yeah, we see the correct one now. Yep.
The correct one. Okay, perfect. Okay, so oops. Now we need to move it. Yes, here.
It looks good.
No, it doesn't want to move. Okay, why is it frozen?
Oh, you mean the slide won't advance?
Yes.
Here we go.
Okay. Yeah. Okay. So I assume that you got a feeling for what NLP and CL, computational linguistics, are, but I just wanted to make sure that we're on the same page. Basically, this is the field of making computer processes process natural language. Processing natural language input data and producing useful information could be natural language output or structured data. And it's basically software that can recognize, analyze, and generate text and speech. Does process entail understand? That's a good question. What do I mean by natural language? That typically refers to language spoken by people, such as English, Japanese, Swahili, as opposed to programming languages like Java, C++, C#, Python, etc. So what is NLP-CL? NLP refers to processing unstructured data, so typically text in free form, unstructured text. This is in contrast to structured text, like what you see here on the screen, which is like in a tabular format, which allows you to do all kinds of numerical range and exact match, for example, for text queries. So why NLP? You see the screen here. You probably cannot read this, right? I hope not. So what do computers lack? They lack knowledge. So computers sees text in English and Arabic the same way you saw the previous slide. People have no trouble understanding language, however. That's because we have common sense. We also have reasoning capacity and experience. However, computers have no common sense knowledge. They have no reasoning capacity, but we can teach them. So why should you care? An enormous amount of knowledge is now available in machine readable form as natural language text. Conversational agents are really becoming an important form of human-computer communication. And much of the human-human communication today is mediated by computers. So really a whole slew of very cool stuff and with lots of commercial interest. So current real-world applications include things like search, think about very large corpora such as Google, question answering, IBM's Watson Jeopardy, translation between languages like Google Translate, summarization across documents, sentiment analysis, if you want to get reviews of restaurants, of movies, products, dialogue systems, blog analytics, where you data mining for blogs like discussion fora, or user groups, opinion data for product marketing, polling, social network analysis, and trending. All of these things are of relevance and very important and have a huge market value. Even more, so speech processing, common sense knowledge, text categorization, web monitoring, etc. Where does NLP fall in the CS taxonomy? So it's right there next to robotics and search. And typically it sort of like encompasses information retrieval, machine translation, language analysis, and so on. Who uses NLP? So big companies as well as small companies, but like the big ones like Amazon, Google, Apple, Facebook, Microsoft, Twitter, etc. They all play in this sandbox. Why is NLP hard? So here are some of the headlines that you get from natural language. And you would see here, like farmer bill dies in house, Iraqi head seeks arms. As speakers of English, we probably understand what this is intended to mean. But as a computer, you can think that this is an Iraqi head and it's looking for arms, as in the human arms. So we know that this is a hard problem. What is it? It's basically relying on ambiguity. So ambiguity in spoken language, something like I made her duck, could be I cooked waterfowl for her, I cooked the waterfowl that belongs to her, I created the ceramic duck she owns, I caused her to quickly lower her head, etc. So there are multiple meanings that could be assigned to this little statement of 4 words. And it could direct you in a very different way if you're doing machine translation, for example. So how do you figure out which one of these senses it is actually alluding to? So why does ambiguity arise? Ambiguity arises from the existence of multiple possibilities, multiple levels of linguistic knowledge requiring resolving ambiguity. So thinking about the phonology, the way the language sounds, the morphology, the lexical items that are chosen, the number, the words, the word order, the semantics, and the pragmatics, which is basically the usage of the language. So why is NLP difficult? Think about these things, like just if we think from an English-centric perspective, some of these things actually appear in natural language. Great job at Justin Bieber. We're so proud of you, and so on. So non-standard English use. So for example, this elongation, segmentation issues, knowing where to put breaks between words, idioms, and so on. But this is what makes it all fun, we believe. So what is the approach to the challenge? We typically divide and conquer. Like good computer scientists, we break the problem into smaller problems, throw state-of-the-art techniques at the smaller problems, and keep our fingers crossed. What falls into the NLP toolkit? There are lots of things. So as David had mentioned, it's an inherently interdisciplinary area of research. So you need to have some knowledge of linguistics. NLPers call them features. There are all kinds of techniques, starting from state machines, formal rule systems, logic, like first order logic, predicate calculus, probability theory, machine learning tools. But essentially, we also have to care a lot about performance metrics as a science. We need to have a well-defined evaluation metric battery for the different tasks that we embark on. The algorithms run the full gamut, from rule-based systems like symbolic parsers, morphological analyzers, finite state automata, to probabilistic and statistical in nature, learning from observation of quote-unquote labeled data, but observation of data in general, and looking for patterns and predicting new data based on the old observations. And essentially, this leads us to machine learning, where you have traditional machine learning and deep learning, which is kind of all the buzz right now. So just to give you an idea of what are the big trends in machine learning, you have unsupervised learning, you have reinforcement learning, you have supervised learning, and they each have their own frications or bifurcations, like classification versus regression, clustering versus dimensionality reduction, and so on. Now, in this big world of artificial intelligence, you have, you can think about them as concentric circles or ellipses, as I have them here. So you have artificial intelligence with machine learning sort of embedded in there, followed by neural networks, and then further in you have deep learning. And basically, deep learning is the bigger trend right now in our field in natural language processing. And it was sort of like revived around, I would say, 2012, 2013, with some initial seeding coming in from the machine learning community at large around 2008, 2009. But deep learning, just to give you a very, very brief synopsis, is inspired by the brain. And the idea here is that you have the cell, the body of the cell, the nucleus, and dendrite associated with it, and then you have the axon and axon terminals. This was sort of mimicked in this architecture where you have the inputs, the various inputs, and a bias feeding into a function, a mapping function, giving output and leading to results. So in this framework, you have simple networks where you have an input layer, followed by a hidden layer, followed by an output layer. And then in deep neural nets, you end up having, you could actually multiply these internal layers into multiple layers. So this gives you like the depth, that's why the word deep comes into the neural network vocabulary. So traditional ML versus deep learning. Traditional ML relied on what we call feature engineering, where people used to sit down and do feature representation for every single feature in the input signal. And it could be typically appropriate for smaller labeled data sets, more or less interpretable. So you know which feature you injected, led to what result? To some extent. So it was more or less, I would say, a gray box or almost a white box where it could actually understand why these decisions were arrived at, compared to deep learning, which is basically feature representation. So you don't need to encode any features, but you need to have the data in such a way that it could be learnable. And it's typically very data hungry. So you need large amounts of data. It typically has huge number of parameters. And in most cases, actually the majority of the cases, they tend to be black boxes. Black boxes meaning that they're opaque. You cannot tell or explain or interpret why did the machine arrive at a specific decision. And it has significant carbon footprint. So in the spirit of thinking about responsible natural language processing and responsible AI, as David had alluded to earlier in his opening, this is something that we also as practitioners tend to think about a lot these days, with the awareness of what does it mean to have TPUs and GPUs running with billions of parameters, which is typically the case right now. And in terms of equitability and equality and access and so on, they have all kinds of other implications. But in reality, they also render superior performance. So this is something that has been taking the field by, I would say, by the reins. And a lot of us now work in deep learning, whether we like it or not. So finding alternatives is another opportunity. But in that spirit as well, we have a whole paradigm that was initiated around this. And I would say it was not intended to be just for mitigation of these huge parameters for training and so on, but also in spirit of how can we use the data more effectively, given that we have small amounts of data in reality. So there's a whole paradigm called transfer learning, where originally, if you have 3 tasks, you'd have 3 separate learning systems in traditional machine learning. But in transfer learning, you have maybe 2 or 3 source tasks. You get some knowledge, you learn some parameters, you have a new task, you apply these parameters to this new learning system. You don't have to retrain, but essentially you transfer information from source language tasks, from source tasks to the target task at hand, and hopefully you get better performance. And there are lots of paradigms and lots of frameworks that have been initiated around this, but the very famous one here is Mr. BERT, and they all have these Simpson names like Ernie, Bert, Grover, Elmo, and so on. But they're variations of the same idea where you have pre-trained sequence-to-sequence models or transformer models, but essentially that doesn't matter what I call them, but essentially these are deep neural network language models that are pre-trained on previously observed data, and then you just take them and apply them for the new data task that you have at hand. So where is language technology today, the status? And actually, this is just sort of like I would say like a pictorial of where we are today. And of course, it summarizes huge amounts of research in this field. It has grown tremendously. But I could say like the first column is mostly solved, things like spam detection, part of speech tagging, where you are assigning a part of speech like an adjective, noun, verb, and so on to text. Named entity recognition, person, organization, location. So Einstein would be a person, UN would be an organization, location would be Princeton. This is mostly solved. And we're making good progress in sentiment analysis. Basically, best roast chicken in San Francisco will be a thumbs up versus the waiter ignored us for 20 minutes, thumbs down. That's kind of what we call sentiment analysis, a classification task. We're making good progress there. Co-reference resolution, word sentence ambiguation, parsing, machine translation, information extraction. So that's making good progress. Still quite hard is areas like question answering. So how effective is ibuprofen in reducing fever in patients with acute febrile illness? That's kind of a hard question to respond to, especially how and why questions. So we know how to do factoid questions of what, why, where, what, where, when, but when it comes to why and how, it's more challenging. Paraphrase detection, summarization, dialogue systems are still also very hard. And this is the picture for high resource languages. So think about the caveat for the pictures for high resource genre and languages. The picture is much different for low resource scenarios. So in low resource scenarios, we're still making progress in one, and it's still quite hard to do progress in the second column, and it's still very hard to do progress in the third column. So before moving on, I'd like to make some terminology note before I get to the meat of this talk. So what is a corpus? It's a collection of text. What is a parallel corpus? It's typically a corpus of two languages in translation aligned at the sentence level. So think about the Bible, the UN proceedings, the proceedings of the Hansard proceedings of Canada, where they have English and French. What is the comparable corpus? It's basically two corpora corresponding to each other, discussing the same subject from the same time frame, but not really aligned. So think about the New York Times and the Wall Street Journal. A domain is the subject matter of the text, so politics versus sports. A genre is the writing style reflecting levels of formality, for example, like newswire versus blogs versus tweets. These are different styles of writing, so this is what we refer to as genre. A language is such as English, French, Arabic, Swahili. A dialect, or what I refer to typically as a variant. I don't like the word dialect, but I'm just going to use it because it's kind of the nomenclature. Moroccan Arabic, Egyptian Arabic, Canadian French, Brazilian Portuguese, etc. So ideally, what is our desiderata? In a world of globalized communication, we'd like to have a universal solution with a local flavor. And why is that important? I think, again, giving equal access to everybody in the world is something that I think as a technology we are responsible for. So think about this. Data is really the gasoline of the 21st century. Almost, as I mentioned, 90% of the data is unstructured, and there's a new era of data flooding. It's really a genuine treasure trove of information out there and of knowledge. So what is our mission as people working in this field? We'd like to convert this data into valuable information. So think about data science and analytics. Natural language processing combined with machine learning could help us go achieve that mission. And we happen to be extremely lucky. We have the alignment of the stars. So there are advances in algorithms in general and ML in particular. And also something that tends to not be mentioned very often is the ability to finally go beyond the toy systems to build robust, large-scale, tractable systems. And that's thanks to the hardware advances in this field, in hardware, computer hardware. So we're living in a very nice alignment of the stars, kind of a eureka moment in our history. So, but successful machine learning relies on data, as I mentioned, is data hungry. And I mentioned that current trends of deep learning are extremely data hungry. And ML is really a pattern recognition problem, really. So pattern recognition relies on redundant signals, frequent patterns. However, in a world of unstructured data, we have many domains, many genres, many languages, many dialects, many variants. So these are what we call data scenarios. And many of these data scenarios lack automated digitized data. Even if a lot of data exists, we have a lack of processing tools, lack of sufficient financial compute power for all scenarios, especially depending on where you come from. So there is also a problem of democratization and a problem of equal access, problem of equal compute power, so or equitable, let's say, as well. And there's a lack of labeled data, as I mentioned earlier. Supervised approaches still significantly outperform unsupervised approaches. So there's a ubiquity of these low resource scenarios. So one approach is to devise solutions for each and every scenario, which needs lots of labeled data per scenario. And as I mentioned, again, supervised systems still outperform unsupervised ones. And you have too many varieties, too expensive an approach. So I would contend that low resource scenario solutions are really one of the NLP and ML next frontiers that need to be addressed. So what is the case for Arabic? This is about an Arabic workshop after all. Arabic is not just one language. It's, I hope, I'm assuming that Nizar or Walid or Wasim, any of the speakers before had probably delivered this message, that Arabic is a multitude of variants. You have dialects along social, geographical, demographic dimensions, not to mention other dimensions. And the variants that we have lack standardized orthography, not enough, and you can think about this from a machine learning perspective, you don't have enough frequent signals. And you have things like Arabizi, you have a lot of code switching, and user-generated data is mostly in the variants. But you say, okay, so basically you can think about it as Arabic as an NLP low resource microcosm, NLP low resource. So you have the whole problem of low resources embodied in Arabic per se. So, and I also contend that to solve problems for Arabics leads to more robust NLP solutions, more generalizability. But wait, we have a lot of modern standard Arabic resources, thanks to DARPA, QNRF, and some industrial funding. So what does that mean? Really, NLP for news, is that good enough? Yeah, but we also know MSA is no one's native spoken language. So why care about user-generated data? First off, few genre exists in this modern standard Arabic, Newswire formal language. And realistic use cases are in dialects. Think chatbots. I mean, yes, we do have them speaking to us back in Fusha in modern standard Arabic, but how awkward is that? First off, it's awkward because it's not realistic and it becomes concocted. And I work now for Facebook, and I can tell you that a lot of the translations that we produce, I sit down and I'm like, huh, what? What is that about? It's really, really hard to get your head wrapped around it. So it's important, but also there's a responsible NLP component to this, where we have equitable information access and use by all Arabic speakers, all. And we know that modern standard Arabic proficiency is really sort of, I want to say not exclusive, but it has a lot to do with your education level. And given our education level today, it's and the fact that it's not anybody's native speaking language, it is actually barring people from having access to information that they could have at their fingertips, especially if it's in their right variant. So one approach to this, now that we've laid out the problems, one approach to this is how to convert one approach is to convert all the dialectal variants to a standard. So basically the idea there is to amplify the signal. As I mentioned, you have low resource scenarios where you have a huge tail of the distribution, and and the signal becomes very faint, therefore it makes ML very challenging. So how do you do that? You just standardize the variants into some standard, and that way you boost the signal, boost the frequencies, and you end up having a better machine learning framework to learn patterns. So that's one approach that I was involved in at some point in my life, where we worked on a problem called CODA, which is, and we had a tool, in fact, called CODAFI. In fact, this is work by Iskander et al. From 2013. And the idea there was to standardize dialectal variants into one standard form, or multiple standard forms corresponding to Egyptian, corresponding to Moroccan, and so on, which is great. But the problem is you write too many rules for normalization, and it's not really that scalable. You have too many real varieties. I mean, you can be idealized and say you're going to only work on Cairene Arabic, but wait a second, what about those who come from the south of Egypt? What about those who come from the north of Egypt? What about those who come from Sinai? What about those who come from the desert, closer to Libya? And technically, I think maybe, I'm not sure what Nizar presented today, but I would assume he talked about the continuum of the dialects, urban versus rural. So there are so many dimensions by which you can slice and dice this picture. So coming up with rules for everybody is kind of a hectic job. So an alternative perspective is not treat variance as noise. So the perspective that was adopted, at least I was thinking of when I was attacking this problem, thinking of dialects as a noisy situation, but rather embrace this variability and treat it as generalizability. And once you think from that perspective, then you try to come up with the right kind of hammers in order to, perfect your attack on the nail. So what are some alternative approaches? This is what I'm going to be talking about a little bit today, and give you a flavor of some of these approaches. Typically, they fall under the unsupervised and semi-supervised realm, and they kind of hint on a little bit of transfer learning. So basically, I'm going to talk about generalized models, and I'm going to talk about character and subword level representations. And I'm going to talk about a method that I tend to, or an approach, sorry, or a paradigm that I refer to as Robin Hood, stealing from the rich to help the poor. And in this way, you actually tend to be more equitable in your allocation. So the idea there is to exploit aligned bi and multilingual resources such as parallel corpora, unrelated corpora dictionaries, knowledge bases, and so on. But also another approach would be around exploiting linguistic affinities such as language families and varieties. So I'm going to talk about three sort of big subsections here. So the generalized models. So basically, this is the problem of token level language identification. So intrasentential, or what we call linguistic code switching. So we have the sentence in French that starts in French and it ends in English. Je vais à la marché, on foot with my son. So the stuff that's in blue is actually a different language. So you have French with English. And this is a very pervasive phenomenon that you get to see in all bilingual and multilingual communities, where people mix codes, mix languages from, together. And they even mix registers. So, you could start in formal language and go into informal language and so on. So this linguistic code switching, this is a slide that Nizar and I had worked on ages ago. So in this, the reality, if you listen to the text, it's actually, if you listen to the speech correlated with this text, it's come from Al Jazeera. The red stuff is all in Levantine Arabic, which is a variety that's spoken in the Levant, which is like Syria, Lebanon, Jordan. And this is the reality of it. Nizar is a native speaker of the language, so he actually was the one who, marked what's red and what's black. And basically, the problem is, if you actually submit this to a machine, this blue stuff, which takes the red and actually it takes the red and turns it into blue, is in fact things that look like modern standard Arabic, but they're in fact dialectal. They're actually Levantine. And this is a problem because things could have different meanings, whether they're in modern standard Arabic or the dialect. So this is a problem. So identifying the code switch points, where does the code for dialect stop and where does the code for modern standard Arabic begin, is a very, very challenging problem. So lots of approaches have attacked this problem, as I mentioned, as a token level, token meaning word level, problem of text identification, language identification. One approach that we had built back in the day was Lily. And essentially, this was an independent tool for token level language identification. And we meant for it to be something that would be cross-linguistic. Basically, the assumption under Lily is that each language has its own character pattern, behaviors, and combinations relating to the underlying phonology and phonetics and morphology. And the ideal solution is that you would get per language a closed set of impossible letter sequences, which should help in distinguishing between languages within an utterance, but also in reality. It is hard to find such sets for all languages. So the practical solution is to do character level n-gram language models. N-gram means sequences of letters for a target language, maximizing the probabilities of the possible patterns and suppressing the probabilities of the impossible ones. So basically with this setup, we're basically approximating such a closed list. So we had 6 language pairs in our corpora. Language 1, so you had English, Spanish, Nepali, English, Nepali, modern standard Arabic, Egyptian, English with Arabizi, which is basically Arabic written in English in the Latin script, and Arabic with Ngari, which is basically English written in Arabic script, and English Hindi. And these are the language sizes. So we had the percentage of language 2. So language 1 would what we call a matrix language, and language 2 would be the embedded language. And essentially, looking at, especially for Arabic, modern standard Arabic with Egyptian, 17% of the data was actually in Egyptian. For English Arabizi, only 10% was in Arabizi. And for English Arabic Ngari, we had almost 0.03% was in. So it's a really, really, really low resource scenario compared to what we had in language 1. So this posits really, really challenging problems for this problem. So Lily was basically, the idea was to leverage simple features to train a conditional random field model. This is traditional ML that classifies each token to any number of in any new input sentence. And basically the idea there was we used 5 gram, basically the size of the n-gram was 5 letters for each language. And we apply all of the created CLM to each word in the input sentence to find their character sequence probabilities in each language. And we also had for the matrix language for language 1, a unigram word level LM language model. So the intuition there is to increase the difference between the feature vectors of the words related to language 1 and those related to language 2. And we use only the WLM on the training data, only on one on the training data. And we apply this WLM, word level LM, to each word in the input sentence to find their word level probabilities. So just to give you a sense of the results, Lily, in general, outperformed the best published results except for modern standard Arabic and Egyptian. In fact, the best published results now are around 92%. And it also came from our lab. In fact, it was Muhammad Badrashini, the co-author in this work, was also co-author on the other one. But compared to also majority baseline, we also see significant improvements over the majority baseline. One thing, for extremely low resource languages, Lily significantly outperformed majority baseline and best published results for English Arabizi, and also for English Angari, which was pretty nice compared to the baselines. And as I said, IDA2, which was the current existing technology that people have been using at least until 2018, was around 92%. We also wanted to show that for Egyptian specifically, if you just focus on language 2, you'd see that Lily did in fact outperform the best published results specifically on language 2. So it was 88% versus 82.9%, which is also something, it's a significant margin. So basically, given these results, we said, okay, what if we just threw everything together? We just converted everything into Latin script, and we threw everything together and see how well do we perform. Do we need to do any really serious hand tailoring across languages? And to our surprise, what we call Lily Multi outperformed Lily Binary and best published results in majority baseline, if you think about the average F-score. So in fact, for Egyptian, we still outperformed best published results, and even by a little margin, we also outperformed for Ngari and for Egyptian. So Lily Multi benefited from having the multilingual signal in the mix. So what is the takeaway message here? Character models combined with simple word level models are very powerful for token level language ID, especially for languages with very low resources such as Egyptian and Ngari. So I'm going to talk about alternative approaches, the Robin Hood approach, which I think is the most interesting part of this talk. And the idea there is how to exploit aligned resources, such as parallel corpora, unrelated corpora, dictionaries, and knowledge bases. So the general protocol is in a classification task across languages is to do what we call label projection via parallel corpora. So what I call LP, label projection. Given a sentence-aligned parallel corpus, rich resource together with poor resource, use an off-the-shelf classifier for the rich resource, project or map the induced labels from the rich side to the poor side of the corpus. So you just project it because you have alignments across words. So you're able to project, or across sentences, so you're able to project. And use the resulting label data. So now that you've created a corpus with labels, albeit noisy because they're projected from the English source, sorry, not the English, the rich resource, it could be English, obviously, to induce native poor language classification model and apply this new resulting model to new data. So you're able to do predictions. So that's one big general protocol that people have been using across, but this is contingent upon having parallel corpora. Another approach has been looking at word level cross-lingual mappings. And basically the same idea, given a sentence in a poor resource language, map the sentence itself, the sentence words, to a rich resource language words via cross-word mapping techniques, something like static bilingual dictionaries, leveraging cross-lingual word embedding mappings, and so on, and apply this rich language classifier model to the map-induced sentence. So I'm just going to do a little small detour here to give you a flavor of how to go about doing that. So in the mapping of word sentences to rich resource language words, basically this leverages a technology called cross-lingual word mappings, and they could be word embeddings. And this is the technique that I'm going to focus on for the coming 2 minutes. So in unsupervised cross-lingual word mappings, the assumption is that distance between word vectors reflects semantic and syntactic relationships. And semantic relationships tend to be more prominent than syntactic ones. So the hypothesis is semantic relationships must be consistent across languages, given comparable data. So just to show you how this works, just look at these two, sort of like matrices. These are matrices of word embeddings that are calculated from comparable corpora and French, and these are Newswire. So look at these two matrices, they look almost the same. They're very, very similar. And these tend to be English to French translations compared to when you just choose a random selection of words from French, you see the matrix looks very, very different. And this is even held more if you look at French, the distribution of a word like go together with its surrounding words looks very similar if you look at pairwise distributions of go with other words that are related to the word go. In French and in English, the equivalent looks quite similar. Same thing with refuse, told, say, Monday, office, China, and now tend to be even more consistent than verbs. So this is a nice observation, and this observation was made way back when in 1998, but then it was further operationalized in the modern statistical NLP in 2018 and 2019. So basically the idea is if you have an initial set of words, you're able to learn mappings across languages. So you're looking at pairs of words and you're looking at their relationship with each other, and you're hoping that they would map to each other in some space. But how do you find this initial set of words that you can start from? Because initialization is very important. We look at word frequency as a way of the assumption is that word frequency partially correlates with meaning. And the parallel distribution of words is consistent across languages. So just to prove this point, frequent overlapping word distributions if you look at the first 1,000 words in French, English comparable corpora, and you look at their translations, around 82% of them are translations of each other. So this gives you a very powerful observation here. So the distributions follow this trend. So in the second 2,000 top frequent words, around 50% of the words are actually translations of each other, and so on. So just to give you an idea, examples of word vectors in the original vector space. And if you think about ways of manipulating these as spectral manipulations, you can end up seeing some kind of interesting phenomena. So the word lundi, which means Monday, was very far away from the word Monday here, but once you apply the spectral embedding mapping, you end up getting lundi closer in the space to Monday. And once you see the closeness, you're able to project that they are actually similar words. So just to give you a sense, here is actually I'm just going to skip straight to the Arabic. If you look at what we've done, so we have the word like Ulia, which means supreme, the translation supreme. If you look at parallel data, it mapped to the word high. If you look at comparable data, which is not necessarily parallel data, you get the word supreme. Diplomacy, diplomatic, means peaceful and justice. Tawsiya means expand, expansion, boost, and so on. So basically, the idea here is that if you have these spectral initializations, you can find these correct mappings for a limited subset of words, But basically, to generalize to unseen words, we fit this linear projection matrix given the extracted pairs. And we expect that the errors would be overcome in the process. So in the results here, if you start with completely supervised mappings, you actually end up with this blue line. If you start with our approach, which is unsupervised, where you derive the mappings through these frequency manipulations and transformations, you get very similar performance. And if you're completely starting from random, this is the performance. So this is very, very promising. And we found this within parallel corpora. Once you go to comparable corpora, the distance increases a little bit between the ideal situation of supervision versus non-supervision, but the distance is not too horrible. So it's actually something that could be managed. And to give you a sense of where things go right and when things went wrong, so words like hawar, you have negotiation, argumentation, dialogue, and basically it was mapped in the parallel corpus to dialogue, consensus building, intra-east, and in the comparable corpora to dialogue, peace, conciliation, reconciliation. Migalla was mapped to co-author, publishes, journal, magazine publishes, etc. Some of the incorrect ones were actually quite interesting. So you have things like claim, requirement, which is equivalent to matlab, was mapped into principled, insists, insisting, insistence, objection, demands, refusal, deference. Binaya, which is basically a building or an edifice, was mapped into floors, tower, dormitory, parking, 3-story, 6-story. So related senses, not really completely out there. Another famous contemporaneous approach that was that appeared on the market was cross-lingual word embedding mappings using, but this was typically, it had both supervised and unsupervised, and it was by Kano et al. And the idea there is that you manipulate, you take words in one space and words in the second space. So think of this as language X and language Y, and you manipulate them. You manipulate the matrices, the vectors of the matrices, as in certain ways, and you actually end up having gato and cat mapping to each other. So to the task that we have at hand, we have emotion detection. And emotion detection is a classification task. I love the Big Bang Theory sitcom. The people who refuse to wear masks really get on my nerves. These are, both could be labeled as joy and anger respectively. And we took this and we basically wanted to evaluate which of these projection methods works best for these low resource scenarios. So the baseline is a monolingual supervised system. So you train on data that's labeled and you predict on on data. And we took the label projection via parallel corpora approach, and we also did the direct cross-lingual word mapping via unsupervised transformations, which we call DCLM. And we used, in this case, the Muse setting. And this was for languages. The rich resource language was English, and the poor resource language was Arabic, Odia, and Ilocano. So these are really, really low resource languages, and the Arabic was specifically dialectal Arabic. And the results that we got were actually in the range of as follows. So the baseline was around 30% for Arabic, which tells you how difficult this problem is, and 38% for Ilocano, for Odia, and Ilocano 40%. And we applied a very sophisticated by LSTM framework, which actually gated RNNs for the language projections, the label projection problem. And then we used the same architecture, same deep neural network architecture, but using, instead of an LM and LP, we use DCLM, which is basically these word embedding mappings cross-lingually. So you don't rely on having parallel resources. The numbers go up for the DCLM. So it's around 37% for Arabic from 30%, which is a significant margin actually. But it shows you that there's a lot of room for improvement. But also it shows that these direct word level mappings are very, very useful. So they were consistently outperforming the label projection across the board. But the label projection also, and both of these approaches significantly outperformed the baselines for both Odia and Ilocano. So this is really nice. We believe the problem with the Arabic was the fact that the data that we had was, the parallel data that we had was actually the Bible and Quran and Newswire, but the test data was in social media. So this is an issue. So the genre difference made a big difference here in this case as well. So I'm going to talk a little bit about the last part of my talk, which is basically exploiting affinities such as language families and varieties. And this was in the machine translation scenario. So the idea was, if you only have a machine translation system in one variety, which is in this case modern standard Arabic, what do you do if you have test data that's in a completely different variety? So going from in-domain training data to out-of-domain test data. So this was basically using an exclusively machine translation system to translate DA Arabic. So we exploited a phenomenon called false friends, or faux amis. And the idea is, for faux amis, you would have similar spelling, but different meaning. So just to give you an idea here, you have the word gift and gift in English versus gift in German, which means poison. And it's a false friend because it has a similar spelling, but and also has a different meaning. So this is a false friend. So basically the idea is, if you have a word like zay or z, zy in standard Arabic, it also only means uniform or clothing. But if you go to dialectal Arabic, the most frequent sense of that word is such as or like. And it also has the other sense of z, but it's really less, it's more of a marked sense. So that's why it's in red. So it's less frequent. So the idea here in the context of machine translation is like, if you see the word zay in your source, what you end up doing is basically you try to replace it. So how can we go from a robust SMT or machine translation trained exclusively with standard Arabic into producing a good quality translation if you have these words in there which are quote unquote noise or variance of the language. So the idea would be to actually replace it in place. But how do you actually discover them? So I'm actually going to skip a little bit here. And the idea here is to discover these by looking at contextual embeddings, looking at the context in which a word appears, and identifying these words as like, oh, they have multiple senses in the MSA, in the dialect. And the fact that they have these multiple senses tells us that they have multiple ways of being rendered. So, and then once you find them and you have them replaced. So in the interest of time, I'm going to skip over a lot of this. And okay. So for the experimental setup, we had basically an evaluation. We wanted to use this as an evaluation of a false friends detection. So identifying when these false friends occurred. And we use translation as a way of doing that. And then we also used evaluation metrics that are standard for machine translation. And our evaluation data was Egyptian, and our training system was completely modern standard Arabic. So this gives you an idea of the different baselines that we had. We had a no replacement baseline, a random baseline, and a blind baseline. And we also had the replacement strategy. So how do you replace and when to replace were two things that were taken into consideration. So we wanted to compare the results. So with simple replacement, we see slight improvement over a random baseline and a blind baseline from 20.6% to 20.7%. Higher blue is better. The other metrics, anything that has ER in it, tir, were, per, all of these, the lower is better. So we see very modest gains in performance, but we do see some gains. But also what we note is compared to the different protocols that we used with no replacement baselines on data, we get 21.3 in blue for the baseline, and we see the best performing one of our models gets you at the same level. But what we see significantly is that the word error rate goes down from 68.6% to 68%, which is a good thing. But doing a little bit of error analysis, as good scientists would do, I wanted to see qualitatively, are we getting really better translations? And in fact, we were. So you see here, like the reference translation is let us forget about our differences and unite. The baseline translation, we disagree and suffering from, but once you do the replacement, let us leave our difference and unify. So this is a much better coherent translation. We see also here, and those who said that the girls, indeed, I heard very bad words, why? And the base translation would be, and to say very, very difficult, this is why I heard. But in the replacement translation, and to say seriously, I heard strong bad words, why? So this is more coherent, as you can tell. And same thing, instead of the word thub, instead of it was translated as health in the original baseline translation, but in reality it means temem, which is okay. It was translated as okay. So these are all very, very promising results. So today's state of the art, emotion detection in English is around 60 to 70%, depending on the genre. Arabic is still at 37%. Machine translation, if you think about high resource scenarios, whether these are high resource languages or genre, we're looking at 70 to 80% blue, while Arabic is still in the low 20s. And this is as of July 2020 from the commercial systems that are out there. So I think we should view this delta as an opportunity. Remember, our desiderata in a world of globalized communications is to have universal solutions with a local flavor. So reality is, digitized labeled resources only exist for a handful of languages and genre. If we solve the problem for Arabic, you have solved the problem for the majority of 7,000 languages in the world. So this is a good thing to look for. I hope I've convinced you that Arabic is a microcosm of NLP and even pushes the ML technology because basically you're trying to come up with generalizations, and that's what makes this a very interesting science. So also one little tidbit, transfer learning was really invented for these low resource scenarios. So my word of wisdom, seize the opportunity. And thank you very much. This work was supported by funding from these different agencies, and I'd be remiss if I don't mention my collaborators on this work. There's Mariam Aminyan, Mohammed Rasuli, Hanan Al-Darmaki, Mahesh Mohan, Mohammed Badrashini, and Shabnam Tefrishi. And thank you very, very much for your attention.
Mona, the one thing I miss most about Zoom is the absence of ability to applaud. We know that we can put up silly yellow hands that clap, but I just want to, on behalf of the couple of hundred people who have stayed with us into this late hour here, and this very early hour for you, I just want to thank you for a fascinating tour. Really, I love seeing all the subtleties that, you know, are common sense for human, and being able to appreciate not only how hard they must be for a machine, but also what sophisticated tools are called upon, you know, to try to make progress. So I personally haven't heard you speak for a while, and there's a lot going on. So thank you for that. I love the universal solutions with a local flavor theme.
Yes.
I love the choice of Arabic, because although it's characterized by you as a low resource language, doing anything with it has such a high payoff compared to some of the very
Exactly.
obscure languages. You know, so many speakers with different dialects, but you know, if you could make progress, it would not only be intellectually interesting on behalf of those few thousand other, very small use languages, but it could be commercially useful. So.
Absolutely.
There are some questions in the chat box, a couple of commendations, but also questions. I'm sure we all have some, but let's go through these from the general audience first. Zayed Al-Fai has basically a question about, you know, in what respect is Arabic low resource? Because there are a lot of data sets in sentiment analysis, but is it in summarization, question answering, entailment, and so forth? And then he asks a second but related question: is the cross-lingual transfer a solution that you're proposing, or just an interesting research approach for now?
Mm-hmm. So on the first front, yes. So this is a problem. A lot of people think that Arabic is actually considered what we call mid-resource, because there are lots of resources for it, technically speaking. What people don't realize is that we have a lot of modern standard Arabic resources for it. And thanks, as I mentioned, to efforts by the funding agencies across over the years, Arabic was of interest for strategic reasons. But but when people talked about Arabic, they actually were referring to modern standard Arabic, in fact. When you think about the dialects, it's low resource across the board in the sense of, think about how many data sets exist for Tunisian, for Moroccan, for Yemeni, for any of the tasks. We have bits and pieces. It's a very fragmented picture. So it's a very spotty map, if you want to think about it this way. So technically speaking, when I talk about Arabic, I mean the whole bouquet of Arabics. I'm actually not referring to one variety per se. If we're just focusing on modern standard Arabic, yes, we've made some headway, especially when it comes to parallel data for modern standard Arabic. We have even blogs. So if you think about translation, for example, translating social media, and I could say this as somebody working at Facebook, when you translate social media, our translation tends to be into modern standard Arabic. Occasionally, we get the fluke situation of it being translated into Egyptian, into dialect, but never have I seen it to date translate into Moroccan, into Tunisian, and the same thing applies to question answering, entailment, summarization. And I've worked on every one of these problems in depth, both looking at Arabic and other languages. We significantly lack resources across the board. So now cross-lingual transfer in low resource settings, solution, is it a solution or not? I think it is a solution. And especially, I did not talk about some of the results that we're getting, for example, in emotion detection, with just basically fine-tuning on, which is basically the paradigm of transfer learning, just fine-tuning on small amounts of data, we end up getting really good results, which in fact are on par with tailored systems. So this is a very promising direction, and I feel like it also has commercial viability. So it's not just a matter of doing it for academic contemplation. It actually pays off in industry, and I mean, without divulging too much, but yes, this is a very viable approach. Now, but also cross-lingual transfer. So there is zero-shot learning as well. So think about mammals, like other paradigms that I did not talk about, which are also very, very promising, and they scale nicely to situations. The problem that the cross-lingual transfer and so on, the approaches that are relying on large pre-trained language models have the impediment of, not being able to retrain them in a very simplistic way, unless you're the Googles and the Facebooks of the world. So this is one of the problems that I see going forward, and that's why we've been looking into alternative approaches that don't rely on such huge underlying machinery. But the concept of transfer learning is still, I think, very viable in even industrial settings.
Great. Many of the students who have been participating with us today are undergraduates in the computer or information sciences. How accessible is, a frontier research project in NLP, in your view, for an undergraduate computer science preparation, presumably at GWU? This is a question that you've, maybe there's been, some supervised projects or whatever. Could you give some advice on, entering this field at that level? Or is it really something you should, get a master's degree and maybe even a PhD first?
So actually, I would say even high school.
Okay.
So not even. So I get access, inquiries from high school students, especially those who come from magnet schools in the US. And we're very welcoming. In at least GW is very encouraging on that front, but also it becomes a factor of the people's time bandwidth. The faculty's bandwidth. But there's nothing barring. In fact, we encourage that. And at Facebook, and I know that this was the case also at Amazon, where I worked before Facebook. There are certain tracks for computer scientists, computer science undergraduates. They go under the software engineering track, but they actually could say they want to work with an NLP team, and they in fact work on things that result in papers right away. So this is something that's very amenable to, and it's international, it's global. It's not necessarily only focusing on the US. So showing that you have good work ethic, that's number one. And you're serious about being diligent, about, and being coachable. I think these are two important traits. And once you show that in the way you write, in the letters of recommendation that we request, then you definitely have a chance. And we have, at least to my knowledge, there's nothing that says you have to have come from the Stanfords or the Columbias of the world. You can come from everywhere. And that's across the board. I assume that the audience here is from all over, so I'm not even going to talk about KAUST and the excellent programs that you have.
Thank you. That's very encouraging. I take it that's because there are enough good tools now that anyone who has an interesting hypothesis and maybe some access to some data that hasn't been used before can therefore make a real original contribution. That's an exciting
Absolutely.
state for a field to be in.
In fact, thank you for mentioning this. I'm comparing to when I finished graduate school. So I finished graduate school in 2003. And I remember us we had to code SVMs. We had to actually write the code for that, HMMs and so on. That's why we know these so well. And I wrote Perceptron. So it was something that we actually had to implement ourselves. Now you have the right tools. You have PyTorch or Keras, and you just go in and you manipulate some of these algorithms and stitch them together. Of course, I would encourage that you actually acquire a deep understanding of these things in order to know how to manipulate them the right way. But yes, the tools have made life so much easier for the current students. So it's really phenomenal.
That's very encouraging. By the way, a couple more questions have come up, as well as more commendations. One participant wants to know about transformers on NLP. Use a model for English and try to do a transfer learning on Arabic with one of these new, I guess, GPT 2 or 3, whatever. So what do you have to say about that, besides destroying the environment with all the energy?
So they were almost approaching trillions of parameters for these. It's absolutely crazy. But yes, we actually have been using transformers, in fact. So I talked about our published work, but we've been looking at transformers as another paradigm. And yes, definitely. BERT is based on transformers. BART is based on transformers. So that technology is already embedded there, and this is the sort of like the crux of how we do pre-trained language modeling. And now within Transform, I don't know, according to my understanding, the audience is still undergraduate, so they probably don't, I don't want to be talking too much jargon. Yeah. But basically, what we do actually, we tend to manipulate the objective functions for the pre-training. So if you are able to pre-train, then you can change some of the objective functions. So within transformers, within BERT, for example, the objective function is masked language modeling, where you take every, like around 15% of the words in your language, you mask it, and the task becomes a prediction of this masked token. And that's how you train these models. Now you can manipulate that task and make it a different objective depending on what your task is. So say, for example, summarization, then you could mask phrases, you could mask whole clauses or sentences. So there are all kinds of techniques that we play with transformers in for this cross-language transformer, cross-language transfer paradigm or learning framework.
Thank you. Some of the questions that are coming up are, I think, inspired by you, but best answered locally, like what sort of PhD spots do we have here? Although maybe you want to say that for yourself too. But I would just like to perhaps, well, one question is, will your slides be available actually? Or,
yes.
Okay, maybe if you send them to Jiangliang or Inji or Mohammed, that they can make sure that the registration list has access to them. Because there are many things that went by very quickly, of course, but
I'm sorry there were too many.
It was very efficient use of time. I remember now how fluid your speech is in so many languages. But I wanted to make one other comment, which was something you raised at the very beginning after my introduction. You said, by the way, it's, it may not be that there's a high percentage of women in computer science now compared to the growth of the field, but in the beginning it was, a women-dominated field. So that made me start to think. Of course, Ada Lovelace, very famous, Grace Hopper, pioneer in programming languages, Anita Borg, Fran Allen, who we just lost in compilers. Is there sort of a resource, an inspiring resource that you would like to point to there, or should students just go Google on their own? For discovering the largely female prehistory of computers.
So actually, one of my, I think of her as my role model, and she's a common friend, Kathy McEwen.
Oh yes, of course. We actually were hoping to hear from her as well, and we will again in the future. She's been here once. Yeah.
Yes, she's an amazing woman, a trailblazer in so many different ways. Apart from establishing whole, research trends in our field, but she's done a lot for women at Columbia. Probably you know about her work, about how she, was one of those women who helped women in their careers, how to balance family life with academic life, the tenure clock, and so many different things on a sort of like professional level. So I feel like she's one of the trailblazers in our field in general. So yeah, she stands out to me as a role model, actually, among other lots of other great women, but especially Kathy McEwen. Yeah.
Thank you.